I'm putting negatives in there. And I have a triangle 4. Now I'm going to do everything about the base or x-axis. Now, why in the hell is he doing this about the base and the x-axis? Because I want to be able to not have to think about, hey, what's the di, the distance from the centroidal axis of the rectangle to the overall x-axis of the figure. Those are my di's. I don't want to have to deal with take this, half of that, divide by this, subtract from that. I don't want to think. Okay, I want to make this life easy for myself. So, this is a copied column from the centroid. This was 38.485, 42, minus 14,137, and 14. Yup. This is copied from the centroid, which are my y bars, because I'm going to the base, or the x-axis. If you go back to when we did the centroid, this was 2.971, 3.5, 5.726, and 2.333. Now I'm going to square these to get this number. 8.826, 12.25, 32.787, and 5.442. Notice how quickly I can fill in this table on the bottom. Now I'm going to multiply those two numbers together to get 339.701. These two numbers together get 514.5. These two numbers give minus 463.51. These two numbers together get 76. Sum this column. 446.891. I mean, seriously, the effort it takes to fill out the bottom table, the area moment of inertia table, with using the base as where I'm going to take and find the I values, really easy. Two columns that are copied from the centroid. That's just a simple squaring. And that column right there is two columns multiplied by together. The first column is nothing. The first column is formula. ICG for a quarter circle. 0.05488 R, in this case 7 raised to the 4th. That's going to give me 131.742. Rectangle, 112, base, 6, height, 7, quantity cubed. What's being cubed? Well, we're going through the axis that goes through the center of that area. What's being cubed is that distance right, that's the perpendicular distance, which happens to be the 7. That's going to give me 171.5. Quarter circle, that's going to be 0.1098 R. R is 3 raised to the 4th. That's going to be 8.894. And the triangle 136 BH cubed, that's going to be 4 times 7 quantity cubed, 38.111. Sum this column, 332.459. Add these two columns together, and I will have I about the base, or I about the x-axis, equal to 799.35. If I want to find the ICG using the parallel axis there, XX, will be I base minus AD squared. That's going to be 799.35 minus the total area, which comes from the centroid, 80.348, times the distance squared. What's the distance? Get it from the base to the centroid. That would be my y bar. Exactly. And I already know my y bar is 2.65. Which gives me ICG XX is equal to 235.11. 235 through the centroid, parallel to the x-axis. This is about the x-axis, or the base. Notice the base is almost 4 times as large as the one through the centroid. So the centroid I is not the largest I value you can have. It's actually the smallest. Okay? Now, I don't know what other people teach. I don't know how Stokes teaches it. But I like this where I don't have to think about these DIs. And the reason I do this is because I noticed as I kept teaching this class, holy shit, all the errors seem to be because students can't get the DIs right. Remember, what are the DIs? The DIs, so this is the centroid location for this individual piece, 3.5. Well, the centroid for the overall figure sits over here at 2.65. So I technically need, that is the distance that I need. The distance between the centroidal eye for the figure that I'm looking at and the centroidal eye for the overall figure. That's the pain in the ass. That's where students were creating error after error after error. So what I tried to do is, you know what? Let's eliminate that error for you by sending everything to the base, which means all the DIs of my y bars. If I'm sending everything to the y-axis, then all my DIs will be my x bars. And now I don't have to sit there and think about what the hell is this distance. No need anymore. Got it? Now, so what we just found was the I through here is 799.4. The I through the centroid of the figure, which is parallel to this, was 235. I'm going to give you an alternative. And if you're comfortable, if you feel comfortable with it, then use it. It is very much usable, but only if you're comfortable. If you're not comfortable, then stick to something that you know until you get comfortable and you can modify later. Here's something that I want you to be aware of, and if, like I said, you're comfortable, then by all means you can use it. If not, don't use it, stick to what we just did. Okay? Let's go back to these formulas. Everybody see these formulas? Now, there's lots of formulas. 1, 2, 3, 4, 5, 6 formulas there. Right? Notice it says this is the x-axis for the rectangle. Agreed? But it also says, hey, if you want to know the I about the x-axis, the base, it is bh cubed over 3. What I used in the calculation was bh cubed over 12, which goes through the I bar, which is the centroid. Now, if you look at this diagram, this rectangle here has a location on the base. So if I really wanted to, rather than go through the ICG, I would go in there and use that 1/3 BH cubed, and I'd already be at the base. So what would my DIs be? Zeros. I'm already at the base. Same thing with the quarter circle. It has a base. The I about the quarter circle base sits right there. You can see it. So the I, what I did was I said, here's the I through the centroid. I used, what the hell was it? 0.05488 R to the 4th. If I go about the base, notice, Ix equals Iy, which is pi R to the 4th over 16. Same thing with the triangle. Here's the triangle. The I about the base would be this guy, BH cubed over 12. And now all my DIs would be 0, 0, 0. Okay? The only thing I have to worry about is this semicircle, which is not on the base. Is it? So I could do, hey, the I that goes through here, and then send it down to the base. So it'd be the only one I have to worry about. The only one. So I would say 0.05, no, for the semicircle is 0.1098 R to the 4th. And then I would send it with a DI of 7 minus 4 times 3 over 3 pi. That would send it to the base. So if you looked at base formulas, this is what you would write. Here it is. I'm not saying you need to do this. I'm just saying this is an alternative. Let me zoom out. There you go. Now you can see the whole thing. So notice for the quarter circle, I use the I about the base. Pi R to the 4th over 16. What are my DIs? 0, 0, 0 all the way across. Why? Because you're already at the base. The rectangle, I used BH cubed over 3. That's already about the base. So what are my DIs? 0, 0, 0. For the triangle, I used BH cubed over 12. What I used before was BH cubed over 36 because I went through the centroid. Now it's over 12. What are my DIs? 0, 0, 0. Why? Because you're already on the base. I don't have to shift it down to the base. It's already at the base. The only one I had to shift was the quarter circle, or the half circle. Notice I used 0.1098 R to the 4th. The R is 3 raised to the 4th. That gave me 8.894. It's a cutout, so I have to put a negative. And now, since it's not on the base, I have to shift it down to the base with a 7 minus 4R over 3 pi to get me to 5.726. Now add everything together. That gives me 1262.935. This gives me minus 463.608. Not the same values I had before. Add them together, what do I got? 7.99327. What did we get when we did it? About the base using the ICGs. We got, where the hell did it go? Here it is, 799.35. Same answer. Same answer. But the approach was different. Notice, look at the formulas for the I's. 131,742, that's the I that goes through the centroid of the quarter circle. This is 471,496. That goes through the bottom of the quarter circle. This triangle is 171.5. That goes through the centroid. This one, 686, goes through the base. This one, minus 8.894, it's the same because I use the same formula, ICG. 38.11, no, 114.33. So these are the base formulas, these are the formulas going through the central. What happened when I was on the base? I didn't have to transfer. 0, 0, 0. The only one I had to transfer was the semicircle to send it from the top down to the base. Okay? Do you see the difference? No. I'm not saying you need to do that. I'm saying if you're comfortable, you don't need any DIs. But at the same time, I didn't make it that hard by sending everything through the CG and then all the DIs are your Y bars from the central. So which way you want to do it, it doesn't really matter. You get the same answer. It's whatever you are comfortable doing, is what I'm saying to you. But as you get better and better at this, you should know how to do it different ways. Here's the number one error that's going to happen if you do it this way. You're thinking, okay, I need to do this about the base, I need to do this about the base. So, here's what's going to happen. Are you ready for this? You're going to say quarter circle, let me see my sheet, about the base. That's pi r to the 4th over 8. So I'm going to use pi times 3 raised to the 4th over 8. And then I'm going to send it with a DI of 7. So in my solution, no, this is the wrong one. In my solution here, I will have a DI which is 7, and this would be the same as it is now, 0.8894. What's the problem there? It's not correct when you put 7 here. Why not? Why not? Well, because you didn't obey the parallelogram. What you're saying is this, which is completely wrong. I got I about the base, and then I'm going to transfer it, multiply times AD squared, where DI is the 7. Well, I about the base is equal to ICG plus AD squared. You need the ICG, not the I about the base, in order to transfer. The parallel axis theorem is very, very specific. It does not say IA equals IB plus AD squared. It says IA is equal to ICG plus AD squared. You can't transfer willy-nilly. It's a remote axis and a centroidal axis. It's not two remote axes. Okay? You with me? All right. We're going to move on to this one. This is the first time that you see something to the left of a coordinate system. And we're going to do this one by doing the centroid and the area moment of inertia. So we're going to do this by saying, hey, this is area 1, area 2, and area 3. I've already told you that on the test, it's 3 areas or 4. I usually don't go beyond 4. I haven't made the test up, so I don't know if it's 3 or 4 yet, because I haven't made the shit up. So let's do the centroid first. Centroid says I've got a rectangle 1, a triangle 2, and a quarter circle 3. There is no cutout Agreed? There's no cutout here. So, I'm going to come in and I'm going to say area of a rectangle. Well, that's base times height. Base is 8. The height is this, which happens to be the 6 for the R. Well, shit, I don't need a calculator for that. 6 times 8 is 48. Triangle. Half of 3 and a height of 6. So this is 1/2 times 3 times height 6. Well, shit, I don't need a calculator for that either. Quarter circle. This is going to be 1/4 pi times 6 quantity squared. That's going to give me 28.274. Sum this column up. That's going to give me 85.274. So I already know X bar is some number divided by 85.274. Y bar is some number divided by 85.274. That's a fact. Okay, X bar. From the y-axis over to the center of this is how much? Well, half of 8. 4. From the y-axis over to the center of this is going to be 8 plus this little piece right here, which is 1, which is 9. Because what's this little piece? B over 3. Base is 3, divided by 3 is 1. So this little piece is 1 plus the 8. Quarter circle. We're going to go from here over to the center. Well, from the sheet, that distance is 4 over 3 pi, which is 4 times 6 divided by 3 pi. That's going to be 2.546, but it is a negative because it's to the left of my y-axis. If you look at it from the quadrant sake, these are all positives. This is a negative positive. This is a negative negative. This should be a positive negative. So if you have something in this area right here, you should have 2 negatives for the X bar and the Y bar. If you're over here in the 4th quadrant, I should have a positive X but a negative Y. So I could have a cutout piece in the 2nd quadrant, which means I'd have a negative area and a negative X bar, which when you multiply together gives me a positive. You've got to be careful with the positives, negatives. All right, multiply these two numbers together, 192, multiply these together, 81, minus 71.999. Sum, 201.001. 201.001 gives me 2.357. 2.357. Y bars. So from the x-axis up, half of 6, 3. From the x-axis up, that would be h over 3, which is 3 over 3, which is 1. No. That would be 6 over 3, 2, sorry. 2. And then from here up would be 4 over 3 pi again. 2.546, but that's a positive. Multiply these two columns. Please notice how I'm using my fingers. And the reason I'm doing it is because I've seen it over and over. People multiply these two columns to get that. Nope, it's this and this. 144, 18, 71.999. Sum, 233.999. 233.999 is going to give me 2.744. So my centroid lies 2.357, comma, 2.744. There's my centroid location. 5 points on the test to give me this. The next 5 come from the area moment of inertia. 10-point problem, right? 5 for the centroid, 5 for the area moment of inertia. Let's do the centroid. Let's do the area moment of inertia. I'm going to send everything to the base. Now, suggestion as one of your 5 problems, use, since everything has a base already on the x, use the base formulas. Try it. Use the base formula. You should get the same I base that I'm about to get here. And what are your DIs? All zeros, because you're doing it about the base. That's the beauty of it. But I'm going to do it using the ICGs. So, I'm going to copy my areas. 48, 9, 28.274. Since I'm doing it about the base and I'm using the ICG formulas, my DIs are going to be my Y bars. 3, 2, 2.546. That's 9, that's 4. Calculator, please. Because I need the calculator for that one. 6.482. Multiply these two numbers together, 432. Multiply these two numbers together, 36. Multiply these together, 183.275. Sum, 651.275. Wow, that was really hard. That was really, really hard. The only thing I need is the right formulas for the ICGs. Right? For the ICGs, any questions on this? Copy, square these numbers here, multiply these numbers together to get this, add. I'm telling you, if you can add, subtract, multiply, and divide, this should be an easy 100 for you if you're not going to create math errors or you're not paying attention to details. A minus becomes a plus type of thing. Or you forget a minus because it's a cutout. Or you forget a minus because it's to the left of the y-axis for the x. So little things will get you, but it should be an easy 100. All right, here, 112b, b is 8, 6 quantity cubed. Remember, what's being cubed? If you're going through, here's the rectangle, you're going through the x-axis, what's being cubed is this distance, which happens to be the 6. This happens to be the 8. So I cube the 6 and I'll get 144. Triangle 136bh cubed, that's b times 3, 6 quantity cubed, that's 18. Quarter circle, 0.05488, R, 6 raised to the 4th, 71.124. Add these suckers. You're going to get 233.124. Add these two together, I'll get I about the base, or I x-axis, equal to 884.399. That's I about the base. What is it about the centroid? Oh, that's easy enough. I just say ICG XX is equal to I about the base minus AD squared. A is 85.274. The distance from the x-axis to the centroid is my y bar, which is 2.744 quantity squared. Answer, 242.278. Done. How hard was that? What?
Okay, so the very bottom of the page, that's the I about X, right?
That's the I about the x-axis or the bottom of the finger.
The question's asking for about Y.
Huh?
The question's asking for about Y, not X.
Bullshit. Does not say why. You're on the wrong page, son. The next one says it about the Y. Oh, mother of God. He thought he had me. No, you didn't. Now, somebody with a quick calculator for me. I need a quick calculator. Because now I'm going to do it about the base. Just so you can see. Component I, area, DI squared, AI DI squared. Here it is. Somebody got the quick calculator? You ready? Okay. Rectangle. The I about the rectangle is I. What about the base? The base is what? BH cubed over 3. Correct? Okay, so I have BH cubed over 3. What's my base? In this case, 8 times 6 quantity cubed over 3. Give me a number. How much? 576. Triangle about the base. BH cubed over 12. So this is I is equal to BH cubed over 12. Base is, in this problem, 3 times 6 quantity cubed over 12. What do you get? 54. For the quarter circle, about the base. About the base is here. That would be pi r to the 4th over 16. I equals pi r, which in this case is 6 quantity cubed, no, quantity to the 4th, over 16. What do you get? 6 raised to the 4th times 3.142 divided by 16. What? I can't hear you. 71.124. Sum this column up. Because these are all now zeros. What do you get? What do I get? Huh? What do we get? Somebody sum this up for me? What do you get? 884.47. 884.399. Again, it's a matter of rounding somewhere along the line. So do you get the same numbers? Use different formulas, but I got the same damn numbers. You with? Who's not with? Speak or forever hold your peace. Robinson, we good? Carpenter? I have no idea. Which table? This table? What about it? You didn't have all the numbers. Okay, now you have it. What do you got? We're going to go down. Oh, the final answer? You want to see the final answer? There you go. There's the final answer. 242.278. I really don't need this. I really don't, because I project pretty good. What? What did you just say? This might sound dumb. Okay, let's go with the dumb question. Well, am I sending everything down to the base? It's my y bars. Am I sending everything to the y-axis? It's my x bars. It's hard. It's not. We're about to do one for the y. Turn the page. Because my boy over here wanted to do this way before I did this one. So, here you go. Now I want to do it about the y-axis and the centroidal y. Same configuration I already had. We've already done the centroid, so this is done. Right? We did this. It's the same problem with the same thing, so that's the centroid portion. That ain't changing. Now my y's. You ready for my y's? Oh y, oh y. Here we go. The shapes are still the same. Rectangle, triangle, quarter circle. That hasn't changed. Okay? My areas, that didn't change. 48, 9, 28.274. This is from centroid. Centroid calculation. That didn't change. Right? We found that here, 48, 9, 28.274. And that total was 85.275. So this was 85.274. That's not changing. What are my DIs? If I'm sending everything to the y-axis now, they're going to be my x bars. So now this is my x bar. And my x bars were 4, 9, negative 2.546. So copy those over. 4, 9, negative 2.546. Square, 16. Square, 81. Square gives me a positive 6.482. Now I multiply these two columns together, 768. Multiply these two columns together gives me 729. Multiply these two numbers together gives me 183.272. Sum the last column, 1680.272. Bingo. You with? Who's not with? Talk to me if you're not with me. She left. She had a what? An emergency call? Okay. ICG. But now I'm doing it about the Y. So now you look for the rectangle. Now it's the red line. So now I'm going through here, through the CG. What's the perpendicular distance? It would be that, which in this case is B. So if you look, now it's going to be Y bar, I bar Y, B cubed H over 12. So now my formula here is going to be ICG of 1/12 H B cubed. That's 112 times 6 times 8 quantity cubed. That's going to be 256. ICG of 2. That's going to be the triangle. Again, notice I'm doing the red line now. Going through here, through the CG. That's going to be the perpendicular distance. Again, it's going to be the B that's going to get cubed. And I have IY bar B cubed H over 36. So now I have 136 times h times b cubed. That's 136 times 6 times 3 quantity cubed. 4.5. And ICG of 3, that's the quarter circle. Notice, for the quarter circle, it's still the red. But notice, IX bar equals IY bar, which is 0.05488 r to the 4. That didn't change for the quarter circle. So this is 0.05488 r, which is 6 raised to the 4th. That gives me 71.124. Sum 331.624. Add these two together. I'll have I about the y-axis, which is 211.896. ICGYY will be 2011.896 minus the total area, 85.274, times the distance. That distance will be my x bar, which is 2.357 quantity squared, which gives me 1538.161. 1538.161. Now, do this one because everything's everything you can do about the y-axis. Try it. Use the base formulas for what? What?
What is the y-axis?
This is the axis that is parallel to my y-axis, but goes through the center of gravity. That's what ICGYY stands for. It's parallel to my y, but goes through the centroid, as opposed to going through the y-axis, which is what I got when I did 2011.8. That's the I going through the y-axis. Questions, thoughts, comments? How many know AutoCAD? Well, if you know AutoCAD, AutoCAD can do all of this for you. Just got to draw up the figure and tell it to give you the mass properties. This is what it will print out. This is the exact same problem we just did. The area was 85.274, that's what we calculated. The centroid lies at 2.357, 2.744, exactly what we calculated. Here's your y-axis, 2011.96, we just calculated. There's your x-axis, 884.46. We calculated both of those. It calculates the radius of gyration for you. It calculates the I values, 242.0469. So it will do this. So you draw it up and you ask it to find the mass properties of this thing, and it will do it for you. You don't have to do it by hand, but you need to know how to use AutoCAD. Okay? Questions? All right. So that takes care of that problem. This one right here is one that you use integration. I did it so that you can see how you do integration. Well, you need the strips and all that stuff, and then you integrate. And I'm not worried about that. The only other problem is this one on page 173. I ain't going to do this too babyish, but I'll give you the answer so you can try it yourself if you want to. This has an axis of symmetry. So I'm going to put a datum down here and measure everything from the datum up. All you need is a y bar. This y bar turns out to be 5.47. My I about the centroid of the figure XX is going to equal to 467.8. The IYY is going to be 121.8. So if you want to do the X and the Y's, those are the values for it. And all I did is I've broken up into three pieces, namely piece 1, piece 2, and piece 3. 3 different rectangles. I told you about the new apartments that are going up next to the standard. This is one of the beams. This is one of the beams that's going in. Oh, you can't see? Yeah, you can. It is basically a T-shape. So to find the area moment of inertia of this, you make it into one big ass rectangle here, another big ass rectangle there, you cut it off. There's only one hitch. You got to take into account these quarters, circles right there. Because it's not really one big rectangle, another big rectangle. There's a little bit of you can see the curvature in there, and you have to take that into account when you do this problem. And that's the beam from the side. It is the length of the trailer. It's a pretty long ass beam. That is not as small of a beam. And it's all concrete. I just took that picture today because it just showed up on the lot today in the T section. Okay? So, as far as I'm concerned, we are done with area moments of inertia. Moving on. Moving on to friction. Everything you need is in the Pro Copy booklet. Turn the page and you'll see, the first thing you'll see is the definition. The definition of friction. You should know this because you saw this in physics. There's nothing new here. Well, there's a couple of things that are new. Friction. It's a tangential force between two contacting surfaces that resists motion or the tendency towards motion. So 2 things about it. One, it's a tangential force, and it's a force that exists between two surfaces. And it's going to oppose motion or the tendency towards motion. If you have motion, you're going to have a different effect. Now, most people think of friction as bad. Actually, there's a beneficial and a detrimental side to it. In the table, you'll see beneficial forms and detrimental forms. You cannot drive a car without having friction, because that's how you brake. You brake when 2 pads hit the rotor, causing friction, and it stops the rotor from rotating, which stops your car. So friction in that case is a huge benefit to you. Okay? 2 forms of friction, static and dynamic or kinetic. There's the definitions. Still tangent. One makes everything stop. The other is a friction force that is part of motion. Okay? Now, friction facts. Everything's going to boil down to these 2 diagrams right here. Hey, what happened? Here we go. So, the friction facts, the A through H, is nothing more than verbal replay of the graph. So I have a block, and I'm putting a force on it. Friction is going to oppose this motion. If I apply a load and it doesn't move, I'm somewhere on this line. This is equilibrium. It ain't moving. I can add another force. Increase the force. It's still not moving. I will get to a point where the force, I feel it just about to move, and that's when I say, hey, come here, help me push. And all of a sudden, it goes. That point where you almost feel like it's going to go is called the impending motion. On the verge of moving. It is the only place where F is equal to mu static times N. It's the only place. The peak point. Then, once it's in motion, notice the friction force drops and becomes steady. Now, these aren't exact lines. They're data points. You're taking the least squares fit in there. Once it's in motion, F is equal to mu kinetic times N. Where did we get this? We get this from the laws of friction, which come from Coulomb. Notice the word empirical, meaning I can't derive that shit. And until somebody proves Coulomb wrong, we will still use F equals mu n. Just like F equals ma, Newton's second law. I can't derive that. That's an empirical formula. Observed phenomenon. Until somebody comes along and says, yeah, your shit don't work. Who, by the way, who said that? Who said that to Newton? Einstein came along and said, hey, Newton, your shit don't work when I approach the speed of light. To which I'm sure Newton comes back and says, fuck you. Can you see that? Newton saying fuck you to Einstein? Huh? Newton was a religious man? I'm a religious man too, but I say the F word all the time. What the hell? The beauty about being a Catholic, you just go and confess, hey, I curse, sorry. Say a few Our Fathers, go on by your way, done. So, my boy, Newton comes back and says, yeah, but human beings are moving at the speed of light, so you still got to study my shit. And that's why you're still studying Newton's laws. Because we, human beings, don't move at the speed of light. Okay? Really, if you look at everything being said here, in words, it's a summary of what you see in the diagram. Bottom line. All right. A couple other things to finish off the topics. For example, ordinary changes in temperature do not materially affect the coefficient of friction. Ordinary changes in temperature. Ordinary. You started this morning at 68 degrees. It's now up to 86 degrees. That's an ordinary change in temperature. Your car started at 68, but by the time you get to school here, it's in the thousands inside internally. Therefore, that is not ordinary. Okay? That's going to affect your viscosity, which is why you always need an oil change eventually. Okay? Next, angles of friction. Again, there's that same thing. There's your F, there's your normal force. I put in a resultant. That resultant is F plus N. The resultant of F and N is R. And the angle between the vertical and R is what's known as the angle of friction. Now, these two here are derivable. I'm not taking the time to derive it. If you want derivations, read the damn book. The tangent of the angle of static friction is equal to the coefficient of static friction. And the tangent of the angle of kinetic friction is equal to the coefficient of kinetic friction. Derivable. Ain't taking the time to derive it, you just need to know it. Okay? Objects on inclines. There are two angles. One is this theta, which is the angle of the incline, and this is still F plus N. That's the angle of friction. So two angles, angle of the incline, angle of friction. Three statements can be made about the angle of friction along with the angle of inclination. And I state them in verbiage, in words, and then I give them to you in formula form. Tangent of theta is greater than tangent of phi s, which equals mu s. In other words, the angle of inclination is greater than the coefficient of friction, then the block will slide down the slope. If the tangent of the angle is less than or equal to the coefficient of static friction, then the block will stay stationary. And the angle at which it is under impending motion, which means it's at the peak of that stupid graph, that's called the angle of repose. All right? I'm going through this quickly. It's there. You can read it, enjoy it, whatever. Dry versus lubricated. So we're talking about dry surfaces. These are the conditions. If you read the lubricated, it's the complete opposite. Whatever's here is opposite for lubricated surfaces. Why? This is the reason why. Because lubricated surfaces have a thin film between the two surfaces. And it causes that reversal of the dry stuff. Okay? My favorite, belt friction. This is the first time that we're going to relax that stupid constraint which said, hey, pulleys, massless, frictionless. Now we know in the real world, there's no such animal as a frictionless pulley. So in order to take into account that there is friction in the real world, we have this wonderful belt friction equation. Derivable. Volk does a great job at deriving. So no friction, which is what we did early on, we said T, T. On either side of the pulley is T. That's why we use the P method. With friction, now, on either side of the pulley, one side is going to be T1, the other side is going to be T2. Oh, the two tensions are not the same. Nope. Not when you have friction or when you bring friction into play. How are these T1s, T2s related? They're related by this equation. Let's go through the equation. Term by term. Beta. Angle of wrap. In radians. Not degrees. Don't you dare do degrees because it doesn't fit. It doesn't work when you use degrees. What is the angle of wrap? So if I have something like this, this is the amount of cable touching my pulley. This is in essence 90 degrees or pi over 2. That's the angle of wrap. If I'm looking over here, is this much cable wrapped around the pulley? That's 180 degrees or just simply pi. So the angle of wrap is how much is touching the pulley from the cable. Mu. That's the coefficient of static or kinetic friction. So it could be used if you're in motion. Yep. Which you will use in dynamics. Because in dynamics, everything's in motion. T2, T1. Here's how we define T2, T1. T2 acts in direction of motion or impending motion. T1 opposes it. So if motion is this way, that's T2, that's T1. If motion is this way, that's T2, that's T1. Okay? Notes, T2 is always greater than T1. Larger tensile force occurs in the direction of impending motion. That's what that's saying. Equation has nothing to do with the radius of the pulley. It's not in there. There's no R in here. Beta is the angle between angle of the belt contact between the drum or pulley and the in radius. The equation is valid for flat belts around any surface. It doesn't have to be a pulley. I could have a square column and I can wrap a cable around it and it would work. What it does not work for is a V belt. In your engine, there's lots of V belts, and V belts look like this. Cross-sectional view. That is not the formula for this. This has a formula, and it's in the textbook in one of the problems. Okay? So we're talking about flat cables, not belt angled off like this. All right? Questions? Questions? I know I went through it quickly, but you can read this at your leisure. All right. When it comes to problems, this is what I'll do when it comes to problems. Okay? And you'll see it when you look at the testing manual. I do it myself. I hope that you would do it too. I write model. I write type. 2 words you'll see me write instantly. Model. Well, what's the model of reality that we have? Well, we either have particle or rigid body. Correct? And by the way, this is a chapter where you will have both models in the same chapter. You'll see particle model, you'll see rigid body model. So that's why I'm saying to you, the first thing you do before you start solving the problem is identify the model. Is it rigid body or is it particle? Well, how the hell would I know? How do you know if it's a particle or rigid body? Hey, if the block has dimensions on it, it's a rigid body. If it doesn't have any, it's a particle. So the reason I do this is I can say, hey, some force in the x, some force in the y equals 0. If I have a rigid body, then I'm going to write some forces in the x, some forces in the y, and some moments equals 0. So right away, that model, when I write particle rigid body, it's already establishing in my head 2 equations or 3 equations of equilibrium. That's what it's doing for me. Type. Well, that goes to this page on 185. There's a type 1, type 2, and type 3. We'll start with type 2 because that's the simplest. The reason it's the simplest is somewhere in the problem you are told you're at the peak point of that friction versus load curve, which means F equals mu static times N holds. So in addition to your equilibrium equations, whether it's 2 equilibrium or 3 equilibrium, you will add in F equals mu static times N for a type 2 problem. So right away you can see somewhere it says impending motion. So some of the things you'll see: impending on the verge of slipping. It might say without upsetting equilibrium. These are all basically pointing you to the peak point of that friction versus load curve. You with me? So in addition to the 2 or 3 equations, you will write in F equals mu static times N. Okay. The next easiest is number 3, where it says impending motion, on the verge of slipping, whatever. Except now, you don't know whether this impending motion is slipping or tipping over. Well, if it's going to possibly tip over, it must create or must have a moment that tips it over. Particle versus rigid body. Which one can tip? Rigid body. So all type 3s have to be rigid body problems. So these, so here you could tip or slip, must be rigid body. It cannot be a particle. And then type 1, nothing is said. You don't know anything. So what do? you assume it's in equilibrium. And then you write for friction FCAL. And I write CAL to remind me, hey, dipshit, this is a calculation, not mu static times n. Don't write mu static n for a type 1 problem. The friction force is a calculation, must come from your equilibrium equations. You with me? Now, you could have a type 1 particle problem, right? Or sorry, a type 2 particle problem, which means type 2, 1, some force in the x equals 0, some force in the y equals 0 is a model of a particle. 2, you know F is equal to mu static times n. But 3, there might be a cable, and you might have to write T2, T1, E to the mu beta. So you might have to bring in all 3 into the problem. What?
I can barely see the light shining too much.
Me too. I can barely see it too. Can you see it now?
Yeah, I can see.
You're welcome, sir. So you might have to bring in some force x, some force y, some moments equals 0, plus the belt friction, plus mu static times n into a problem. You with me? Who know with me? That's Vedanya thing.